Okay, let's continue. Before the full or formal derivation of Kalman filter, let's do one step. Okay, just see the flavor of the derivations. Okay, so all we need, let's not talk about general term. Let's just look at this example for which you have some number to, some people like to see some numbers, okay? This is a special system. First of all, we don't have U, right? There's no deterministic input. U doesn't change anything of the Kalman filter, at least in a hard way, but it just, it doesn't change. And also we don't have measurement noise. The measurement is almost a deterministic function of state, okay? So again, all the other setup are the same, So our initial state is a Gaussian, and the measurement noise is a Gaussian, and this A and A matrix and the measurement noise are the same, has the identity covariance matrix, and this sigma x, what is it? Oh, this is the initial state distribution, initial state Gaussian covariance matrix, and C is 1 and 2. Okay, now I'm asking you to compute two things, x1 hat and x2 hat. Again, our notation says this is what? The best estimate of x1 or x0 given measurement up to y0. This is the best estimate of x1 given measurement up to y1. So these are already the Kalman filter. Okay? Although you don't see that, it looks like another probability exercise, but it's indeed Kalman filter already. Okay? It's different a little bit from previous example because I'm gradually adding more element, let you to see the flavor of the proof. Okay, first of all, let's do which one? Let's do the first one. Expectation of x0, okay? So x0 hat is expectation of x0 given y0 equal to 1. Okay, how to compute this? X, Y are jointly Gaussian, right? So we need to find first, okay, that's 1.1. We need to find x0, y0 joint distribution. Do we have it? No, we don't. We know x0 is Gaussian, and we know y0 is defined in terms of x0. But I didn't tell you their joint. You need to tell me the joint first before we can move on. Okay, so we know these two, the distribution, but we know these two is jointly Gaussian, right? This is a jointly Gaussian, which is have this mu. This is, I will call it EX0, EY0, right? And we'll have some covariance matrix that we need to compute, right? Do you know how this thing is constructed? This guy will be covariance of x0. This is the covariance of y0. This is the covariance of x0 with y0. This is covariance of y0 with x0. This is so small, this is 0, okay? There's no magic because I told you the x0 could be R3. In this case, it's R2, right? Could be R3, y0 could be R10. Either way is fine. The way we structure is just the way we partition this matrix. And this part will mean that. Okay? I think after a few examples, you will be feel more comfortable about this. So let's try to compute what we need for this joint distribution. For joint distribution, it's Gaussian, so we need to know its mean and covariance. This is the big covariance, right? Let's look at, let's see which one. So we know, let's do one by one, okay? We know EX0 is given, right? It's 0. What's the dimension of X? Dimension of X is 2, right? So it's 0 and 0. You have to make sure this vector dimension is right. No, hold on. X is 2-dimensional? Yes. Okay. And what about EY0? So it will be C will be 1 and 2 times 0, 0, which is 0. It's number. The dimension has to be correct. That two things are simple to construct. Now let's look at what's the covariance of X0. Which is sigma x, right? So this is 2, 1, 1, 1, which is the sigma x given in the statement of the problem. You with me? Oh, by the way, I see some students have. Why the structure of the covariance matrix like this? So yeah, how to argue, how to prove? By definition, okay? Of course, why not? You can see what's the covariance. You want to find the covariance of X0, Y0 with itself. Okay, you partition it, you will find it out that's the case. Just imagine this is X1 and X2, X1 and X2. What about this? This will be X1 with X1, this is X1 with X2, right? X2 is the same thing, it's a block operation. Okay, I think that should be enough. Okay, let's look at covariance of X0 with Y0. How to compute it? Will be covariance of X0, C times Y0. So will be, C times X0 will be C transpose here. Okay, so will be 2, 1, 1, 1 times 1, 2 C transpose, which is a column vector 4, 3, right? Yes, okay. Then I need to compute Y0 with X0, which is the transpose of the previous one, which will be 4, 3. The only thing left is covariance of Y. Covariance of Y with itself, right? So that's what? It's a C times sigma X C transpose. I jump one step only, right? It's covariance of CX0 with CX0. So C will be moved out to the left and to the right. The one to the right has a transpose. Okay, so this will, I think it's 10. Okay, we have everything we need for this thing. The joint distribution is specified. As long as we know it's jointly Gaussian, we can compute conditional expectation by our formula now, right? So our formula tells us X0 hat is expectation Y01 is the unconditional mean, which is EX0, which is 0, 0. Let me write the formula, right? So EX0 times covariance X0 with Y0, covariance of Y0 inverse times surprise. How much surprise we got? Y is 1, right? So 1 minus the expectation of Y, which is 0. So the surprise is 1. Okay, after plugging all of that, I think we can find it out. This is 0.4, this is 0.3. You can verify this number. The correctness of this number, I don't care, right? So you should care. We have one-step Kalman filter. Everyone can do one-step Kalman filter now. The initial step. you know, any kind of induction type of proof, the key is how to move from one step to the second step. After that, it's done, right? So let's see, the next part is the most challenging one, or the fun part. By the way, you will see later on we need to compute this P of 0. Okay, you will see, we know how to compute this, right? And you will see where it will be used later on. P0 is what? Covariance of x0 with x0 given y0 equal to 1. How to interpret this? Is given y0 equal to 1, x0 is still random, so its covariance will be based on that randomness. So how to compute this? So it's we have the formula. Okay, so the formula is unconditional covariance. Once you see some relative variable, the covariance changes. Okay, the minus what? Minus the covariance of x0, y0 times covariance of y0 inverse times covariance of y0 with x0. Okay, and verify yourself. It's not definition. This verify yourself. This is some number 0.4, negative 0.2, negative 0.2, and 0.1. Where this formula come from? The conditional expectation formula. Okay, let me just make sure you see what I mean. This guy. Okay. Once you observe y equal to small y, okay, x is Gaussian. Like Gaussian, whatever Gaussian has mean and covariance, it turns out covariance has this form. That's it. Okay. So okay, we have this guy, then we can move on. We can move to the next step. The second step, all right? So I want to compute the best estimate of x1 given y up to time 1. What are they? It's the expectation of x1 given y0. y0 is still given. And y1, negative 1. Okay? y0 is given. Now time moves to time 1. You see another number of y1 at time 1. Okay? Given these two measurements, your belief about x1 also changes, right? And that distribution should also be run Gaussian. So we can look at this as if we can write like this is kind of recursive type of writing. But I can write like this. They are the same, right? y0, y1. This is called y1, capital Y1, right? Equal to 1, negative 1. All right. So how to compute this thing? So I will say 1 is the conceptually simple approach. It doesn't mean it's computationally simple. It's just for you to understand it's simple. To do this is like, I will call this batch approach. It's the same as the first step. This is not Kalman filter, by the way, okay? This is one way to compute this best estimate of x1 by what? Find. So how we can compute this conditional expectation? Because these two, x1 and capital Y1, are jointly Gaussian. By our assumption, all the things are jointly Gaussian in the world of Kalman filter setup. So we find joint distribution first. Okay, so it looks like x1 and y1. This is R3. No, sorry, how many? R4, right? This is the two-dimension. This y1, this 2, this 4, right? But partition-wise, I will call this x1, y1. Okay, so I assume this should be jointly Gaussian, by the way. So this will be Gaussian. This will be expectation of x1, expectation of y1, right? So y1 is, let's write more explicitly this guy, right? That means you know how to compute this or not? You should be able to. I haven't derived it for you yet. Okay, now we have the covariance matrix, right? You can compute. This is the covariance of x1. Somehow you should be able to know how to compute this. It's fairly straightforward, although it takes some effort to find those numbers. Then x1 with y1, right? This is y1 with x1. This is covariance y1. Okay? So this guy is 2 by 2. Do you understand that? X is two-dimensional vector, right? This guy is 2 by 2. This guy is 2 by 2. 2 by 2 because y1 is also two-dimensional. This guy 2 by 2, and this guy is 2 by 2 as well. If you zoom in these 2 by 2, what are they? Those are covariance of y0. This is covariance of y0 with y1. I don't want to write it. It's terrible. Okay. Y0 with y1. This is the covariance of y1 with y0. Covariance of y1. Okay. So if you zoom in, that's that. We don't have to do this. So after do this, do you know how to compute? If I compute everything here, so then we can find expectation of x1 given y1 equal to 1 negative. This is just another exercise. Okay, what is it? Unconditioned mean plus covariance x1, y1, things like that. All right. What's the potential drawback of this approach? Right? It's not recursive, I would say. It's not recursive, not scalable. So as k increases, as k go to 1, 10, 100, 1,000, then the covariance matrix grows. It's huge, right? If you have let's say this y become y100, then you have 100 by 100 this part. Just this block is 100 by 100. So you need to keep inverting a larger matrix. It's not efficient, but it's correct. You can do it. Are you with me? So this is the same thing. This is give you the same result as Kalman filter. It's just computationally is not that efficient. Okay, but the conceptually easy to understand. So far, you already understand how to do this now. Okay, so the Kalman filter has another smartness involved. Okay, we just any questions by the way, the notation. 什么问题? Okay, all right. Now the second approach, which is recursive approach, which is just Kalman filter. Okay, that's the key idea now arises. Okay, so let me just say that. So after, I will say after, let me write it down, right? As we write down, you can think as well. So after obtaining the same kind of argument as I always say, after obtaining y0 equal to 1. That's recursive, right? Let's start from the first one. So after we see y0 equal to 1, before I say x0 or x, now I want to estimate x1, right? So I only care about x1. So I will say, after obtaining y0 equal to 1, both, so we're still at time 0, okay? Still at time 0. Okay, both x1 and y1 are random. I specify y0 already, but both x0, x0 is also random as well, but now I care about x1, okay? So both x1 and y1 are random. Can you see that? Of course, they're random. What their random distribution? I would say both of them are random and they are jointly Gaussian as well. Because conditional Gaussian is Gaussian. X1 and Y1 are jointly Gaussian, first of all. And the conditional on Y0, they're also jointly Gaussian. Okay, and they are jointly Gaussian. Okay, i.e., I have a formula like this follows, right? i.e., x1 and y1 given y0, that's the only confusing part, okay? Let's pay attention. Given y0 equal to 1, Yuntian, how do we interpret this ugly looking symbol?
We have observed y0 equal to 1, and but x1 and y1 are still
random, yes, and their random distribution is Gaussian, all right? We need to specify that. So what's the dimension of this random variable? In this example, it's 3, right? This state is 2, and the y1 is 1. I know the state and the y1 are jointly Gaussian. But that jointly Gaussian is different from before. It's after I see y0, I still think they are jointly, well, this is not I think, they are still jointly Gaussian. So any jointly Gaussian, they will have a distribution, right? The distribution is Gaussian, is characterized by mean and covariance, but that mean and covariance will be expectation of y1 given y0 equal to 1, okay? Expectation of, expectation x1 given y0 equal to 1, expectation y1 given y0 equal to 1. Okay, that's the what? The expectation of the state and the output given your knowledge about y0. Of course, how do I move this around? Anyway, where we are here. Now inside here, I will have covariance of x1 with x1, but it's not the original unconditioned thing. It's something happened, will change my belief about x1. What happened? y0 equal to 1, right? Now this guy is y1 with x1 given y0 equal to 1. And this is conditional x1, y1 given y0. How do I move this guy? Anyway, let me zoom in. Given y0, and this is y1 with y1 given y0 equal to 1. I didn't write what y0 is, but you see what I mean. That's the covariance matrix now. Okay, now comes to the key part, okay? So suppose we know, let's say if we know everything in the above distribution here, okay? Everything in this mean and the covariance matrix, suppose we compute them. Of course, we know how to compute them. Then we claim expectation of x1 given y0 equal to 1, and in addition to that, y1 equal to -1 is, can you see that now? Okay, now I have some nested or recursive conditions, right? The first condition already happened. Given that condition, I know on average I will see some kind of x1, I will see some kind of y1, right? If you want to use measurement to estimate the other, you always put them as a joint Gaussian distribution, right? So in this case, I'll claim the whole thing is this is just what? Expectation of this, I will call this unconditioned expectation because you haven't seen y1 yet. Okay? And plus the covariance of x1 with y1, but still given y0 equal to 1, times the covariance of y1 given y0 equal to 1, inverse times surprise. The surprise is -1 minus expectation of y1 given y0 equal to 1. Okay. The only hard part of common filter is just this line. I think you see what it means, but maybe loosely or a little bit fuzzy, but over a few times of exercise, you will see exactly that's the case. Do you understand or you don't? You don't? Yeah, we have homework to practice you on that. Okay. Let me try to explain a little bit more. I'm not sure whether this helps you or not. Sometimes people like this. Sometimes people like, I introduce another notation that can somehow make things a little bit clearer, but other people may hate my notation. But let's try, okay? So let's define z equal to x1 given y0 equal to 1. And q equal to y1 given y0 equal to 1. There are so many equal, but you should know what it means, all right? This is the whole thing. Yuntian, that's my, can you explain this? Random variables. This distribution is the conditional distribution. They're also Gaussian. Okay? Are you with me? The time is at 0 now. I see y0 equal to 1. Then my distribution of x1 changes. And it's still Gaussian. And that Gaussian random variable, I define it as a new variable called z. Is that okay? This is okay, right? If I change notation, maybe something becomes simpler. And suppose we know z and q is jointly Gaussian. Do you think so? They are, okay? As I mentioned, you can always assume in the common filter setup, everything is jointly Gaussian. Now I see what, all right? I see q, so then the jointly Gaussian, let's say that will be what? This is E of z, E of q. And this is what covariance of z with q, covariance q with z, covariance of q. Okay? All right, if I change notation, everything becomes clean. Now what I'm asking you is that expectation of z given q equal to -1. What is it? Very simple now, right? It's the expectation of z unconditioned plus covariance of zq, covariance of q inverse, and -1 minus expectation of q. Okay? This is simple, right? But you should be able to see this is what? Expectation of z. Z is the conditional random variable. It's x1 given y0 equal to 1. This becomes the same thing like this, all right? This is the same thing like this. It just changed. I mean, if you just redefine the symbols, everything becomes clean to you, hopefully. And it may take some effort for you to see this is nothing but the expectation of what? x1, because z is what? Z is about x1, all right? And given y0 equal to 1 and y1 equal to -1, because q is y1. Okay. So if you like, I can change another notation. Is that expectation? This is nothing but the expectation of x1 given y0 equal to 1. That's z, right? And you're given y1 given y0 equal to 1. All right? So essentially, y1 equal to 1. So essentially, there's no given, it's just given y1 equal to 1. So overall, you have expectation of x1 given y0 equal to 1, y1 equal to -1. So you take a y0 as something given already, and you can ignore it. The symbol here, you can ignore y0. You can presume that, okay, I'm leaving the world now with y0 equal to 1. I update my belief, everything become, I can remove this, but I need to update my belief, all right? I will define a new variable as z. Okay, on top of it, I assume I somehow get new information, y1, then that's how I compute this thing. All right. It will take some effort for the exercise. I think next time I will start with another example, somehow will help students to further understand it. And that's the derivation of Kalman filter, almost everything. Let's go through the steps. Okay, so our goal, let's repeat our goal. Our goal is to find xk hat. Okay, and also because each time at a given yk, xk is Gaussian. So Gaussian has what? You need to keep, how to represent Gaussian? You need mean and covariance. Okay. As I mentioned, the Kalman filter is a recursive way to update this. So we need not only that, we need to know how to move from k to k plus 1, right? So that's one step will be go k. First of all, this recursive way, you need to know how to start, right? We can compute this guy. So sometimes these are given. I will say sometimes x0, p0 are given, directly given to you. Okay, the mean is this, and the covariance this is that. It's directly given directly. If not, okay, we compute, right? We compute. We just need to compute what? We just need to compute expectation of x0 given y0. Okay? Well, I didn't specify what number that's given. And also, p0 is covariance of x0, given y0. That's typically easy to compute. Okay, you can use one formula, the conditional expect. They are jointly Gaussian, right? That's the starting point. And given xk and pk, how do we compute x? How do we move one step forward? If we know this, then everything is done. And the whole process can be divided into two parts. Okay, just for you don't have to do this derivation. Sorry, you don't have to divide this into two phases. If you know how to direct compute them, that's fine. But this will simplify the discussion. And it's correct, so we will, but most people will do this, right? They have two states. Suppose now I have given time k, xk is given given measurement up to time k, xk is random. Its mean is xk hat. Its covariance is pk, right? What I want is I want to go here. That's our goal. I want to say, given measurement up to k plus 1, xk plus 1 is also random. Its mean is xk plus 1 hat. This covariance is this guy. I want to move from here to the k plus 1, and I will insert one stage to simplify the derivation. Okay, the first step is xk plus 1 given k hat, and the pk plus 1 given k, right? So k plus 1 given k plus 1, this means that, right? And this guy is k given k. So both the things before the bar and after the bar need to be updated. So I will do that one by one, right? So I first update the one before the bar. This is so-called prediction. So I only have measurement up to k, and I predict my best estimate at k plus 1. And this step is called, the most important and the hard part is the measurement update. Okay? So now this is only have measurement up to k, right? Now I need to go to measurement up to k plus 1. The only difference is what? I have new measurement. I need to change my estimate. So, okay. Now let's first see the simple step, prediction. So that's, and we are given here, okay? That's our starting point, this one. Suppose we know this. Now let's see how we can do the prediction. What we want is k plus 1 given k plus 1 given k hat is expectation of xk plus 1 given yk. How do we compute this? So expectation of, we need to relate k plus 1 with k. So that will be a xk plus b of uk. I dropped the index for a, b, okay? They're deterministic, whatever those index, it doesn't affect our derivation. Omega k or wk given capital yk. What is this? Can I move this out? It's equal to a times expectation of xk given yk plus b times expectation of uk given yk, which is expectation of 10 is 10, right? A number is number, it's a deterministic thing. So plus expectation of wk given yk. Okay, is this 0? Okay, now my claim, or Yuntian said, it's independent, so it's 0. Is that true? I don't think so. WK and YK are independent. Okay, so independent, WK, independent of YK. All right, everything is independent because process noise is independent of YK. All right, now what does this mean? They can tell me that expectation of YK equal to expectation of WK. Right? Why? Because density doesn't change at all if you know it. And this is 0 because of our assumption. Okay, independence doesn't tell me this guy is 0. Okay, the covariance is true, but for this expected doesn't. But we assume that our process noise is 0 mean, so that's why. Okay, this guy's here. What about this guy? XK hat. All right, so overall I have A XK hat plus B of UK, no more. Okay, I have this formula now. Okay, I call it 1. Like a linear system now, right? This equal to this. Why I can break this? That's the property of expectation. And the conditional expectation is expectation. You don't need to, be confused by those given things. It just tell you the density function is not the one without the condition. It's somehow changed. You just need to use the right density function. Everything become a plain expectation. Okay, let's say pk plus 1 given k. That's our covariance, right? So it's a covariance of xk plus 1, xk plus 1 given yk. How to do this? Covariance is, let's see, so that will be let's write it down, okay? Expectation, covariance is expectation of what? Xk plus 1 minus the expectation of that, right? The expectation of this given this, it's xk plus 1 given k hat, okay, times xk plus 1 minus xk plus 1 given k hat given yk. Oh, sorry, this is a transpose, right? Okay. Overall, I can plug in things. That will be, this is A xk plus BUK plus WK. That's first term. Minus this guy we just computed here. So it will be A xk hat minus B of UK. That's my first parenthesis. Times this guy itself, transpose, right? It tells itself, this guy. Then, of course, everything is given. Given is given, right? It's happened already. So overall, I have this got cancelled with, so that's why U doesn't matter, right? That much at least. So that will be what? Expectation of A xk minus xk hat times this guy, plus, let's not worry about those cross terms first. Let's look at other terms, okay? Times xk minus xk hat A transpose given yk, that's my first term. Okay, I'm missing a lot of terms yet, okay? I will this guy minus this guy, right? And I group them and times whatever the corresponding term in the transpose. Okay, so I put this, and also has some cross terms. So for example, I will have expectation of this omega k times omega k transpose given yk, right? And also have expectation of cross term, this minus this times the omega, so will be axk minus xk hat times omega k transpose given yk, okay? And plus expectation of omega k times axk, so xk minus xk hat transpose A transpose given yk, okay? Well, you should be able to write down. It's very simple. They just take some effort. So the first question I'm asking you, what is this? If you move this out, move this guy out, what you get is A times pk. Pk is just the covariance of xk given yk, right? Times A transpose, that's the first term. Plus this term, is this 0? Is this 0?
No, it's not the covariance of WK given
Wk is independent of Wk independent of Yk. Tells me this guy equal to Wk transpose. Okay? And this I will say this is nothing but Qk. The reason is because I assume Wk is 0 mean. Right? Only when it's 0 mean, that's Qk. If it's not 0 mean, if everything is not 0 mean, then we have other terms to subtract. We'll still have the same conclusion. So overall, this is Qk. So this guy is Qk. Now I will say this guy is this random. What is it? This is 0 or not? Yes, this is the covariance of xk with omega k or wk, and this is 0, right? This is 0, and this is 0 as well. Okay. All right, so overall, I have this one-step prediction formula. This is our equation 2. This is 1. This is 2. Okay? That's the Kalman filter. If you look at, I'm not sure the notation. You look at Wikipedia, whatever, you see those formulas. And you can implement this formula very easily. I will show you code next time. But to understand them, that's the effort we have taken so far. You just try to understand them. Are you with me? What we're doing? Prediction. We are trying to find the best estimate of xk plus 1 at given measurement up to time k. Okay, because everything is Gaussian, we can do this very easily. The second step is the hard part. We have 2 minutes, right? Or 1? 1 minute. We can finish this? No. I don't think so. All right. But I will give you some homework to practice. Next time, I'm sure I will test you on the quiz now. All right. So I keep missing my quiz. All right.